All right, so the first part of this section should be a little bit of review from Algebra 2 with your exponential functions, but there are some things that are a little bit trickier. So before I go on to this page, why don't I just review real quick with you just like general exponential functions. So, an exponential function is when you have an x in the exponent, like let's say you have your basic like 2 to the x. That's growth because the base is a 2 and it's bigger than 1. So whenever the base is bigger than 1, you have growth. So when I plug 0 into that, 2 to the 0 is 1. All right, and then a growth problem is going to look like this. It has an asymptote at y equals 0, horizontal asymptote at y equals 0. And if you move the graph up or down, the asymptote moves with it. Moving the graph left or right, you don't have to change the asymptote or where that is. You can just move it left or right, but up or down, the asymptote has to follow. All right. So then if you have your basic decay function, so a decay function would have a fraction for a base, like maybe 1/2, and then x right there. So decay would, same properties, basically you put 0 for x, you get anything to the 0 power is 1, so it goes through 0, 1. All right, so that 0.01 is going to be like our kind of thing that we base everything off of, like our center in a way. All right, now another way that you can do decay is this. This problem right here, you might see that a different way. You might see y equals 2 to the negative x. All right, so anytime you have a negative exponent like that, remember, this is just like 2, it's kind of like negative 1 and then an x, right? So if you remember from before, 2 to the, whoa, what did I just do? 2 to the negative 1, that part right there, well, that's just 1/2. So another way to write a fraction is to have a negative exponent, which you'll see sometimes. So this is really like 1/2 to the x. So if you see something like, y equals 5 to the negative x plus 4, so you need to take out the negative. So factor out the negative, like factor out a negative 1, which would leave you x minus 4, because if you put it back, it makes this right here. And so you know that this is really 1/5 and then has a power of x minus 4. So you might find yourself having to do some exponent work if the x's are negative, and it'll be a decay problem. All right, so back to the regular. Oops. All right, so you know that this is going to be a growth problem, and this thing is moved to the left 3, and it's moved up 5. Now that up 5 is going to change my asymptote. It was at y equals 0, but now it's going to be at y equals 5. All right, y equals 5, horizontal asymptote. All right, and then I had this point right here, but remember I'm going to move it to the left 3 and up 5. So you literally take it, move it to the left 3 and up 5. It'll be right there. All right, and it's always like 1 off, usually like 1 away from your asymptote. And it was a growth problem, so I'm just going to go ahead and draw it in there, and then we'll look at the calculator. Now, you can always find the y-intercept really easy. If you want the y-intercept, you plug in 0 for x. So if I put a 0 right here, I get 2 to the 3rd, which is 8, and 8 plus 5 is 13. So the y-intercept is 0 and 13. This one doesn't have an x-intercept, so I wouldn't have to find it. All right, this guy over here. It's a decay. It's been multiplied by 4, so there's been a stretch to it. The 2 is moving me down 2. So that's where my asymptote's going to be, down 2. So my horizontal asymptote is at y equals negative 2. And let's see, it's a decay, so it's coming from up and going down. Now, whenever you have a stretch, this that point, because remember I said how like that point was like 0, 1. Well, that gets multiplied by this 4. So 1 times 4 is 4. So that's where it would be with the stretch, but then you move it down 2, so then it would be down 2. All right, and so you can figure that out. You can use your calculator also. But anyway, it's a decay, so it's going to come down through there, and I'm not quite sure where the x-axis intercept is, but that's close enough. We'll just look at our calculator for the rest. My y-intercept, plug in 0 right there. Then the 1/3 to the 0 is 1. So 4 times 1 is 4, and 4 minus 2 is 2. So 0, 2. So you can see that also. So, of course, you're always able to grab your calculator and graph that on there. So let's see. 4 parentheses, make a fraction. All right, power x, and then over there, minus 2. All right, so I can see my x-intercept a little bit better. So I was a little bit off, but I'm not too worried about that yet. We'll figure out how to do the x-intercept later, but realize this problem does have one. So I guess, I should have been closer to like right here or something. Should have come down a little bit sooner, but don't worry about the x-intercept yet. But the y-intercept is a definite. All right, this guy, h of x. So I do have a negative x up here. So I need to fix that up a little bit so I can see what's going on. I have 3. I'm going to pull out a negative 1, which leaves me x minus 1 right there, and then plus 4. So this 3 to negative 1, that's really just 1/3. So this is really 1/3 to the x minus 1 plus 4. So it looks like a growth problem, but it's really a decay problem. So move to the right 1 and up 4. So the up 4 is going to change my asymptote to y equals 4. And I take my dot that used to be here. There's no stretch or shrink, so it moves to the right 1 and up 4. And there it is. And it's a decay. So it's coming down through here like that. All right, so let's see what the y-intercept should have been. Probably should have done that before I drew it. So if I put a 0 in here, I get 3 to the 1, so that's 3, and 3 plus 4 is 7. So it should have been at 0, 7. So I guess I could have waited on here and just done that later, but it should have come around to 0, 7, like right there. All right, so it doesn't look too good, but oh well. All right, so let's see what you're going to have to do on your homework. You have to do all these official things, but that first part was just like a little bit of review from Algebra 2. All right, so you have an official graph, negative 2 to the x plus 4. So remember, when you have a negative in front, it reflects you over the x-axis, and then the plus 4 moves you up 4. So you know the asymptote is going to be up here at 4. So there's my asymptote, y equals 4. And it's been reflected. So normally this would be a growth problem. So normally I would have my dot there, and this has moved up 4. I'm going to grow through that. But it gets reflected. So it gets reflected over that red line because that's kind of like my new x-axis. So when I reflect this over, it's here. And remember, don't draw this, but I was going to draw a growth problem right through there. But it's been flipped over. So now it's going to be looking like this. Right, and we're not going to worry about the x-intercept for now, but the y-intercept you can clearly see is 0, 0, 3. So you can get the y-intercept by plugging in 0, or if you get it on your graph, you got it. So the domain. Exponential functions can handle any number that you plug in. You can put anything in for x, positive, negatives, fractions, decimals, whatever, you get an answer. So your domain is everything. You can put anything. So you can write all real numbers or put negative infinity to infinity. Your range, though, on the other hand, is held up by that asymptote. So the range is everything below 4. So I would say negative infinity to 4, and not even touching 4 because it's an asymptote. All right, it's continuous. It's continuous everywhere. As this graph comes down, it still like edges over to the right. So eventually it's going to go all the way to the right, but we'll never see it because it's so slow and moving over. So continuous on everything. There's no holes or breaks or anything like that. Increasing. This graph is not increasing. It starts on the left and it starts to go down, so it's only decreasing. So I have no increasing parts to mention, just for this one in particular. It's decreasing the whole time, so decreasing everywhere from negative infinity to infinity. So you will find that exponential functions, they will decrease or increase everywhere because it's just all the way across the whole page. All right, my end behavior. So this guy's talking about the right side. So on the right side, it looks like my graph is going down to negative infinity. On the left side, it's coming up towards this asymptote, which is 4. All right, so you might have learned this, like if you're in Algebra 2 honors last year, maybe regular Algebra 2, but you might have seen this letter E. So sometimes you're going to see something like e to the x, or later on in this chapter, log base e. So when you see those things, e is a number like pi, and you can look it up and see what it is, but pi is just big, huge, long, irrational number. Well, e is called the natural number, and this mathematician named Euler, but you spell it like this, he kind of worked on that and did some things with it. So they kind of, sometimes they call it his number. But it has to do with a number that is produced when you look at like interest rates and things like that over time. So anyway, it's called a natural number, and you just see it sometimes. And just like you know that pi is 3.14, then e is this number. So 2.71 or 2.7. So every time you see something like that, if somebody says, oh, e to the x, that's just like 2.7 to the x. I mean, it's no big deal. It's just a number, just like pi is. Or somebody says log base e, then it's log base 2.71 of x. It's no big deal. It's just a number. And so don't get all confused and worried about it. All right, so we're going to do some stuff with that. So I have e to the 2x minus 3. So basically, I have 2.71 to the 2x minus 3. So it's no big deal. It's still a growth problem because 2.7 is bigger than 1. So it's a growth problem. It's moved down 3 spaces. Now, this guy right here, that little 2 right there. So I know that you remember that if you have a number in front of your problem, like if you have, let's say we had 2 to the x and there was like a 4 sitting here, you call that a stretch. And if it was a fraction, you'd call it a shrink. So that 2 up with the x, it is going to stretch your problem also. So we're going to cheat off our calculator a little bit because it does have a different effect, especially with this e and everything. It still stretches my graph. But when I plug 0 into this, e to the 0, because 2 times 0 would be 0, e to the 0 is still 1. And 1 minus 3 is negative 2. So I can still tell that this thing is going to cross at negative 2. So 0, negative 2. Okay. All right. So the asymptote is still moved down 3. So there's an asymptote at negative 3. All right, and then it's a growth problem, so I'm just going to kind of draw it over here. And you can check out the x-intercept on your calculator. I'm not too concerned about that right now. Later, we'll be able to do it perfectly when we learn how to solve this with logs and things like that. All right, domain. Always all real numbers. My range looks like it's everything above 3, negative 3. So it's from negative 3 on up. All right, my y-intercept, oops, I put this in the wrong place, didn't I? Oopsie, no. 0, negative 2. Dang it. Oh my God, you just read it on your paper. All right, so horizontal asymptote was negative 3. It's continuous everywhere. It is also increasing everywhere. So increasing on all real numbers or negative infinity to infinity. It's not decreasing. My end behavior on the right is going to infinity. On the left, it's coming down and staying right above negative 3. All right. So the last part of this little section here has to do with some formulas, and you do not have to memorize these formulas. I will give them to you or let you put them on a note card or something, but you have to know what all the letters mean. So this is a formula for compound interest. And you may or may not have seen this before, but let's see what all these variables mean. So A is your amount. It's like your final amount that you're going to have after all the interest is calculated. So you can say it's your final amount. P is your principal. You ever hear somebody talk about banking or something? Your principal is the amount of money that you start with. So we'll put principal. PLE, not PAL, and so that's your starting value. Like, oh, you invest $200 in a bank account and da-da-da, that's what you start with. R is your rate, your interest rate, but you have to remember it has to be in decimal form or it's going to mess us up. And N is your number of times of compounding, and I'll explain that in a minute. So number of, I'll just say compounds. All right, and T is your time. All right, so number of compounds. What I'm talking about here is like in this problem here it says, oh, this is compounded monthly. So in this problem my N is going to be 12 because every month and it's for 10 years and you'll see it in the problem working. Some other words that people use, semi-annually. So semi-annually, it means twice a year. All right, daily, there's 365 days in a year. Bi-monthly, so there's, that would mean twice a month. So if you're talking about like all year long, you'd be like, oh, that's 24 times. Weekly, there's 52 weeks in a year. So sometimes, the problems just mention different things. All right, so let's go ahead and figure this out. So I want to know how much money Justin's going to have in 10 years. So my final amount is, his principal is $300. All right, I got my formula, 1 plus, the interest rate is 6%, so you had to put 0.06 over n. Now, n is the number of times I'm compounding. My unit is years, so monthly would be 12 times a year, so I put a 12. And up top here, I have n times t. So what, because that up top is supposed to be how many times overall your money is going to get its interest rate. And so, think about it. It's 12 times a year for 10 years. That's why you're multiplying those things, so it should be 120. Okay, so I'll just put 12 times 10 so you remember that, but it should make kind of obvious sense to you. All right, so from here, of course, we're going to just get that in our calculator. All right, so let's see, I got 300. 1 plus, make a fraction. And I'm just going to put 120 out there. All right, so there's how much money Justin will have, $545.82. So put a dollar sign, 545.82. Okay, all right. So there is also another type of interest that you can have, and it's called when it's compounded continuously. So this is like every second or whatever it gets compounded. And so when you do this, there's a whole different formula that you use. All right, and so a lot of times people, this one right here, A equals P e to the RT. So I like to think of PERT, like that shampoo PERT Plus or something. Anyway, you don't have to memorize the formula, but know how to use it. Now the problem has to say compounded continuously. Only when that keyword continuously is there do you use this formula. So you'll see it gets a little bit higher of an answer, and over more time it would go higher than the other one even more. But my amount, my principal is still $300, and I have E, which is just 2.71, to the RT. So my interest rate is 0.06 again. So 0.06, and then my time is still 10 years. So I just wanted you to see the difference here. Okay. So just get that in your calculator. Oops, crap. All right, so the E, if you look at it, I have E right there. You also have E right here. So depending, I want to take this to a power. So I don't just want the number E, I want E to a power. So I'm going to go ahead and put in my 300. I'm going to choose this guy on the left. So E to the power should save me from another step later. Then I got 0.06 times 10. All right, and there's my answer, 546 and 64. 546.64. So you see it is a little bit more money than, last time we got 545. All right, so if you did this over more time and less compounds a year, then you would see it grow a little bit faster. All right, so this last little bit is a little bit of application. You could probably use this in your science class and things like that. This one's exponential growth or decay. So here's our formula we're going to use, and when I'm doing the problem, I'll kind of explain it a little bit. And then you could still have growth and decay, exponential growth and decay, but somebody says it's continuous. So depending on whether the problem calls for that or not. All right, so this first example says the population of a town is declining at a rate of 7%, and the current population is 20,250 people. What's the population going to be in 10 years? All right, and it says using each model, so we're going to do each one. So don't write too big here. So the first model, I'm using this guy here. So n is going to be my, my amount in the end, my n0. So just like in science class, when you have like v0 is your initial velocity, this is my initial number of things, number of people. So I got 20,250. And I have 1 plus, my rate is declining. So actually I don't need a plus, I need a minus right here. So minus 0.07. So again, change your rate, it has to be a decimal. And t, my time is 10. So we would put this in our calculator, but I want you to look at something. I have 20,250, and then I have 1 minus 0.07, so that's 0.93 to the 10. So what's happening here is if I'm losing 7% of my people a year, what's happening is I'm keeping 93%. So that should be kind of like logical to you. You don't have to do this 1 minus 0.07. You can be like, oh, if you lose 7%, that means you're keeping 93%. So what's happening is this number is getting multiplied 93% every year. So after you do it one time, then you do it again. And so eventually this original number is going to go down every year a little bit. Okay? So anyway, you put that in your calculator and you get 9,800 people. So 9,800.6, right? So people. All right, so let's do the other one. So decaying continuously. So we have n equals 20,250. And then E this time, so e to the kt. So k is my rate again. So in this case, the rate I'm declining, so you put a negative 0.07, and then the time right here, of course, is 10 years. So you plug that in your calculator, and you would get 10,000 and 055.9. Okay. All right. So, and people again. All right, so this next example, it says in 1980 there were 190.9 thousand reported cases of chickenpox. 2005, 32.2 reported cases, 32.2 thousand. The number of reported cases of chickenpox is decreasing at an exponential rate. So I'm going to go ahead and use this guy here. Identify the rate of decline and write the equation for what's going on. Okay, so it's like I have two pieces of information. Okay, so what happened here is I started with this many chickenpox cases. It went down to here, and it took from 1980 to 2005. It took 25 years to do that. So in a way, I have all the things that I need here except for one thing. My original amount is the 190.9, so I'm going to put that for my N0. I ended up with 32.2. So I'm going to put that here with my ending value. My time is, 10 years does it say? No, I'm sorry, 25 years it took, so that's going to go here. So then I'm going to solve for R. Okay, so let's do it. So my amount I ended up with is 32.2. That goes there. I started with 190.9 thousand. I have 1 plus R, I do not know. And then on the top part, it took 25 years was my time. Okay, so I'm going to divide both sides by the 190.9. So I get 0.1687 equals, I have 1 plus R to the 25th. So you don't often do this, but I need to take the 25th root of both sides. All right, so the 25th root of the 0.1687 is going to equal to 1 plus R. All right, and then I'm just going to subtract 1 from both sides. So let's go to a calculator, because that's a little bit weird, right? So 25th root, you need to press your math button and go to number 5. And I usually put that answer thing in there, so just put 25 up there, and I got 0.1687. So there we go. Then I'm just going to subtract 1 to keep it all nice and clean. So 0.0687. So 0.069, let's say. So 0.069 equals R. All right, so I'm going to write the model. There's my rate. So I got N equals, and my initial amount is 190.9. I'll keep that there. All right, I have 1 plus R. So frankly, 1 plus R will be 1 plus this number, so 1.069, right? Oh, I knew something was wrong. Wait a minute. This was a negative. I forgot that on my calculator. So 1 plus R would be 1 minus 0.069. So that's 0.931. So 0.931. And I got the T up there. So then this is my equation for what's going on with the chickenpox. And if I can put any number of years past 1980 right up here, and it'll tell you how many chickenpox cases I expect there to be. Okay. All right, last one. I promise we finished up in a minute. All right, under the right growing condition, a particular species of plant has a doubling time of 12 days. So if you ever heard of something like, they say, like in science, they say, oh, there's this bacteria has a half-life of 2 hours. So like, half of it's gone in 2 hours and so forth. This is kind of like that. It's a doubling time of 12 days. So suppose a pasture has 46 plants of this species. How many plants would there be after 65 days? All right, so in this problem, I have to first figure out the rate. I don't know what's going on, but I do know it's doubling every 12 days. And so what I can do, you have to use continuous for this, because every second it's like doing something. These plants are, doubling or whatever. So I'm going to be using my n equals n0 e to the kt. All right, now, so use my information. It doubles the original amount in 12 days. So if I keep my original amount, that's fine. I'm going to have double that, so 2 of those, e to the k, and my time is 12. All right, so you can see here, if I divide by n0, this is gone. So I have 2 e to the 12k. Now, you may or may not remember this from last year, and so if you don't remember this, you can just follow in your homework and do this at least, but we'll get it better after we go throughout the rest of the chapter. If you want to get to this part right here, what you do is you take the log of both sides. So since this is an e, I'm going to take ln, which is a natural log, ln here. All right, so when e is next to ln like it is here, they kind of cancel each other out, and I get 12k. And ln2 is just something on my calculator I'm going to get. So when I do this, I'm going to have ln2, I'm going to divide the 12 out, and there is my k value. All right, so let me go to the calculator and we'll see it there. All right, so I have ln right here, 2. I'm going to get that answer. I'm going to divide it by 12. Ah, crap. Sorry, ln2, and then divide it by 12. All right, so there's my k value, 0.058, let's say. 0.058. All right, so here's my formula. N equals N0. So right now, it says I had 46 plants. All right, e to the k, my k is 0.058. It's positive because these things are doubling and increasing. And my time, it says 65 days. All right, so you get that put in your calculator, and you will come up with 1,995.5 plants. So that's quite a bit. All right, so you got to do your homework. Sorry the video is so long, but then another night, go ahead and do your homework. I'll talk to you in class. Bye-bye.